Next, let's prove some relationships involving set operations. Here are 4 examples. First one, let's prove A intersect B is a subset of A. If you don't know how to prove this relation, you can first use the Venn diagram to illustrate it. And hopefully after you draw the Venn diagram, it can inspire you how to prove this relation. Here is the Venn diagram. You can see, indeed, the shaded area is a subset of A. Now let's see the formal proof. If you still recall, in general, if you want to prove A is a subset of B, what you need to show is you pick an arbitrary element in A, then you show that this element is in B as well. Here I use this implication connective to show that if the left side is true, the right side is true. So we are going to use this format for the following proofs. Step 1, we randomly pick an element X from A intersect B. And then what can we do next? Here we're going to use the definition of intersection. And since X is in A intersect B, by definition, we know that X is a member of A and X is a member of B. And now if you think of this as P, think of this as Q, we know that by one of the inference rules, P and Q can imply P is true. And therefore, we can imply that X is in A. We show that for any arbitrary element X, if it's in A intersect B, then X is in A as well. And then by definition of subset relation, we have shown that A intersect B is a subset of A. Next, we want to prove C is a subset of A and C is a subset of B if and only if C is a subset of A intersect B. First of all, we know that there's these keywords, if and only if. So this is a biconditional. To prove P if and only if Q, we can prove P implies Q and Q implies P. Therefore, naturally, we can prove this if and only if relation by 2 steps. And we call step 1 proving the only if direction. What is the only if direction? So when we see the only if keywords, basically the hypothesis is this one. This is the P, and this is Q. So we want to prove P implies Q. What does P say? P says C is a subset of A and C is a subset of B. But the conclusion is C is a subset of A intersect B. So here basically we need to prove this subset relation by assuming C is a subset of A and C is a subset of B. How do we prove this subset relation? Again, we arbitrarily pick an element from C and we want to show that this element is A intersect B as well. How do we show that? First of all, if X is an element of C, and we know that C is a subset of A, therefore X is an element of A. Okay? And similarly, we can also imply from X is an element in C to X is an element in B. This is because C is a subset of B. Now, if we know X is an element in A, X is also an element in B, And by one of the inference rules that we can imply X is an element in A and X is an element in B. Now, by the definition of intersection, if X is an element in A and X is an element in B, X is therefore an element in the intersection of A and B. We prove that if any arbitrary element in C, it must be an element in A intersect B. Therefore, C is a subset of A intersect of B. But we only finished the half of the proof. For the second half, we prove the if direction. What is if direction? The if direction is this would be the hypothesis, and this would be the conclusion. So now we want to prove two subset relations which are C is a subset of A and C is a subset of B by assuming the hypothesis is true. First of all, we pick an arbitrary element in C. And then, since X is in C, by our hypothesis that C is a subset of A intersect B, therefore, X is an element of A intersect B as well. And next, by the definition of intersection, we know that X is an element of A and X is in B. Okay? By one of the inference rules, we know that if you know X in A and X in B, we can imply X is in A and X is in B. And now if we combine this and this one, we can conclude C is a subset of A. If you combine this implies this, we can conclude C is a subset of B. Now finish the if direction. If you combine these two directions together, we proved the original statement is true. Third one, we want to prove two sets to be equal. And in order to prove that, we can prove by two steps. One, we have to show the left set is a subset of the right set, and the right set is a subset of the left set. Thus, we'll prove this equal relation by two steps. First, let's prove this is a subset of this one. Again, it's about proving this subset relation. We'll start by picking an arbitrary element in the left set, which is the intersection of the power set of A and the power set of B. Now, what do we do next? We can use the definition of intersection. Therefore, this implies X is in the power set of A and X is in the power set of B. What do we do next? We can use the definition of the power set. Since X is in the power set of A, what that means is X is a subset of A. And since X is an element in the power set of B, X is a subset of B. Now what do we do? If you recall, in the previous example, we showed that if X is a subset of A and X is a subset of B, we can conclude X is a subset of A intersect B. If you don't remember, you can pause the video and go back to check the example. Now, if X is a subset of A intersect B, what that means is X must be an element of the power set of A intersect B. Now, if you look at the two ends, we show that for any arbitrary element in the intersection of the power set of A and the power set of B, this element must be an element of the power set of A intersect B. And therefore, we conclude that this set is a subset of this set. So we are done with the first half. Again, you can see it's about proving the subset relation. So we start with randomly picking element in the power set of A intersect B, and eventually we want to show that X is an element of the power set of A intersect the power set of B. We will need to imply from this to this. What do? We're going to repeatedly apply the definitions of different operations. First, we use the definition of the power set. Since X is an element of the power set of A intersect B, therefore X is a subset of A intersect B. And now, again, by the second example, since X is a subset of A intersect B, we can imply X is a subset of A and X is a subset of B. Here, by the way, this intersection, this is AND connective. Don't confuse them. And next, since X is a subset of A, we can imply X is in the power set of A. And again, it should be AND. Since X is a subset of B, X is an element of the power set of B. And now, by the definition of intersection, since X is the element of this set and this set, therefore X is the element of the intersection of the two sets. Now, combining these two ends, we conclude this subset relation. Last one. We want to prove if A is not empty and A intersect B is equal to A set minus B, then B must be empty. Now, how to prove this? If you think about all the four basic proof methods, if we use direct proof, we're going to assume these two are true, then prove that B is empty. It's hard to show that a set is empty, so direct proof is not the best option. What about proof by contraposition? So what we need to do is, if this is P, this is Q, we need to show that not Q implies not P. What is not Q? Not Q is B is not empty. Then we need to show not P is true. What is not P? Not P becomes A is empty or A intersect B is now equal to A set minus B. Now again, we run into the problem of proving A is empty. As I mentioned in the direct proof, it's not easy. Therefore, the best one is actually proof by contradiction, because we can take advantage of more information. To use proof by contradiction, we have to identify what is the hypothesis P and what is the conclusion Q. So you can see I have identified P and Q. And proof by contradiction means that we assume P and not Q is true. So now what is P and not Q? This is P, this is now Q. Next, how do we proceed? How can we prove from these three statements to a contradiction? And I'm going to use proof by cases. Note that the proof is not unique. But here, let me explain why I want to use proof by cases. The reason is, by just knowing A is not empty and B is not empty, we cannot really proceed. The only statement we can work on is the second one. But in order to work on this one, we have to make sure they are not empty. Okay, so there are two cases for A intersect B, or equivalently A set minus B. Either they are empty or they are not empty. So next, I'm going to find this contradiction by dividing A intersect B into two cases. The first one is A intersect B is empty. But how can you use this information? A intersect B is equal to A set minus B. This is from the second assumption, right? And because A intersect B is empty, we know that A and B are disjoint. Therefore, A set minus B is just equal to A. Again, you can use the Venn diagram to show why this is true. And next, what do we know? From the first assumption, we know that A is not equal to empty, correct? But now the problem arises. You look at these two ends. We conclude that A intersect B is now equal to empty, which contradicts with the assumption of this case. So now this is a contradiction. This one and this one is a contradiction. Second case, A intersect B is not empty. And since it's not empty, we can definitely find one element in A intersect B. And since X is in A intersect B, and according to the second assumption, X is also in A set minus B. Now, by definition, since X is in A set minus B, X must not be a member of B. But where's the contradiction? Here, since X is in A intersect B, by definition, we know that X is in A and X is in B. Therefore, X is in B. Now you can see, we first show that X is not in B. Now we show that X is in B. Therefore, these two together is a contradiction. Now, combining these two cases, we have shown that for these three assumptions, if they are all true, we can always find a contradiction. And by proof by contradiction, we have shown that the original implication is true.